Okay, so let's continue with the TCP state machine on slide number 10. So this is the combined operation that we discussed in previous slides, that is data session establishment, session termination, and data transfer phase. So here, as we can see, the first, choose a color. Okay, so here whatever is written on the right side is transmitted by us, and whatever is written on the left side, okay, is transmitted by the other end. So with this in context, I'll explain you the state machine. This is transmitted by us. Okay. So the first step that we see, that is the start of the session. So initially we send a SYN. The right side message is sent by us, transmitted by us. So it's a SYN. So we go into SYN send state. In SYN send state, we are waiting for SYNAC from the other end. So here we see that we have received SYNAC from the other end and we transmit ACK to them. So the number on the right side is what we have transmitted, the message on the right side. The message on the left side is what they have transmitted. So this SYN plus ACK. SYNAC is sent by the other end and we send them ACK. So first step SYN, then SYNAC and ACK, and we go into the established state. So this is one path, and the other path shown here is the other end has sent us a SYN. So if you see this, the other end has sent us a SYN, then we will send them a SYNAC, this is what we have sent. We have sent them a SYNAC, and again we go into SYN received state. This is because we are waiting for the final acknowledgement from the other end. So they have sent SYN, we have sent SYNAC, but final ACK is pending. So which is sent by the other end. So other end sends final ACK acknowledgement, and we again go into established state. So these are the two ways through which we go into the established state. Next, whatever is given in the blue highlight in below, that is, say this section. This is the section for the session termination. What are the ways through which the session can be termination, the TCP session? So this is what is explained in this blue highlighted part. So there are two paths again to the session termination phase. As we can see here, if we send FIN, then we go into active close state machine, and these are the states there which we will take a look later. And if the other end sends a FIN, which is in this case, if you see the other end has sent a FIN, the message on the left side, if the other end sends a FIN, we go into passive close. So these are the states in the passive close which we will discuss. So let's proceed with the left part of the session termination. So we sent a FIN. Once we sent a FIN, we go into FIN wait 1. FIN wait 1. We sent a FIN. We go into FIN wait 1. At this point, we are expecting a FIN and an acknowledgement from the other end. So let me draw it. So okay. So if you see this part, the middle line, I'll highlight that. This one. If you see this, you will notice that the other end has sent fin and ACK. So we send fin. In response to our fin, other end has sent this ACK, and he has sent a fin from his end to end the session. And in return, we have sent ACK again. If you see this one, right? ACK again. This is the four-way handshake which we saw in slide number this thing. So fin, ACK, then again the other end has to send a fin and we have to acknowledge it. This is what has been explained here. Fin, initially we send fin, we go in fin wait 1 state. Fin wait 1 indicates waiting for fin from the other end, as well as, yes, waiting for fin from the other end. So the other end sends acknowledgement and then it sends fin and we send acknowledgement and go to time wait state. In time wait, the session remains idle for a specified duration of time. It will go, the TCP session will be closed. Let's discuss the next path. Now in the next path, we send a fin, which is as per this, we send a fin. After that, the other end sends a fin and we send the ACK. We send ACK and other end sends a fin. Other end sends a fin. And we send ACK. Okay. After this, we are waiting for the last step, that is the last acknowledgement from the other end. Because we have sent fin, we have received fin and sent ACK, but we haven't received ACK from the other end. So that is the closing state. And the closing state indicates that we are waiting for the final acknowledgement, the final ACK, which is to be sent by the other end. So other end sends final ACK, we go into time wait and the session is closed. Okay, now the problematic state. The problematic state is fin wait 2. In fin wait 2, again going through the same path, we send fin, as in here, we send fin. We send fin, we go to fin wait 1 state. In fin wait 1, the other end sends an acknowledgement, but he doesn't send a fin to us. So we are waiting for a fin from the other end. So this is what is indicated in the next step, that we received a fin from the other end and we have acknowledged it as well. We have received a fin from the other end and we have acknowledged it. So we go to time wait. So if the session is sometimes stuck in fin wait 2, then the issue is that the other end is not initiating fin from his end. That can be a problem. So the session may get stuck in fin wait 2 if the other end doesn't send a fin. So this is the left part of the session termination, which is active close. Active close. Okay, next we'll go to passive close. In this part, the other end sends a fin and we send an acknowledgement to him. The other end sends a fin and we have sent an acknowledgement. Now we will send a fin, and expect an acknowledgement from the other end. This is the acknowledgement from the other end. This should be blue. So this is, we have sent a fin and waiting for acknowledgement from the other end. So this is the acknowledgement from the other end. And ultimately the session closes. So this is the entire TCP state machine. So the three phases: session establishment, data transfer, and the session termination. So in this diagram, we are focused on session termination and session establishment. Okay, so next we will go to the various network architectures. So we have for collapse core and 3-tier. So we have two architectures in place. So we'll discuss both of them step by step. Okay, so let's discuss 3-tier architecture. In a 3-tier architecture, you will see there are 3 layers. This is the access layer, aggregate distribution layer, and core layer. The access layer, distribution layer, and the core layer. So the access layer is for user termination. All the users, the servers, etc. Those will be terminated at the access layers. So this would be for users or servers. Okay. So similarly, all the access layers will be for the same purpose. Either users or servers will be terminating. Next important characteristics of the access layer, it will be ideally L2 only switching. So in an ideal setup, there will be no layer 3 at the access layer. It will be L2 only switching. Then as and when we terminate the users on the distribution layer, we terminate them on the layer 3, and on the core layer it's layer 3 only. So let's say for instance we have a user here connected in. So for now we have not discussed VLANs, but just understand VLAN as a group where a user may reside to. So VLAN, for example, there are few users in VLAN 100. So those will be terminated on the downlink port here on VLAN 100 as an SVI. So basically SVI is the layer 3 termination of the VLAN. So this VLAN will get a layer 3 termination at the distribution layer, at the distribution switch. Basically what will be configured is VLAN 100 will be configured with the default gateway for the virtual IP of these distribution switches. I understand this can be very unrelated because I have not explained virtual IP as of now, but in order to understand the architecture we need to understand what a virtual IP is. I will tell you what it is. So it may be HSRP or VRRP. We'll take this technologies in the succeeding section in other chapters, but for now only what you have to understand is for VLAN 100 the virtual IP is the gateway, that's it. So it will either be owned by the switch 1 or by switch 2. So we have two switches in stack on both the sides. So this side also we have two switches in stack. I mean two switches connected back to it, not in stack. So switch 1 and switch 2 both have HSRP VRRP technology running, so they represent the virtual IP for VLAN 100. So VLAN 100 users will hit, for example, let's say primarily switch 1 for whatever request they have to say. So they will primarily hit say switch 1. So now since VLAN 100 is an SVI that's having a layer 3 termination, another IP in the same subnet will be configured in switch 2 in VLAN 100, and for example let's say dot 2 of subnet 10.1.1.1 slash 24 1.0 slash 24. Let's say dot 1 is configured on switch 1, dot 2 on switch 2, and dot 3 is the VIP. So that will be the default gateway for VLAN 100. So when switch 1 goes down, the ownership of the VIP will be transferred to switch 2, and for VLAN 100 the packets from the southbound, that's the users, will start terminating automatically on switch 2, and from switch 2 it will be carried to the core layer, that is the layer 3 only part. So this is how we will terminate layer 2 and 3 both at the distribution layer. So here we'll have L2 and L3 both. So ideally we terminate the layer 3, the layer 2 of the access layer and distribution layer. So access layer is layer 2 only. This layer 2 boundary will be present at the distribution layer, and above from the distribution to the core it will be layer 3 only. So the topmost layer, that is this, it will be L3 only. So this is the 3-tier architecture where we have 3 layers with different roles: access layer, distribution layer, and core layer. Okay. Next is the collapse core architecture. In the collapse core architecture, what we are going to do is we'll merge the functions of 2 layers into one. So what we have studied in the 3-layer architecture is access layer, layer 2 only. Distribution layer will terminate the layer 2 of access to itself on the southbound connections, that is this yellow colored connections, and uplink it will be layer 3. Uplink this will be layer 3 for the 3-tier architectures. So this will be layer 3 at the uplink. Now in collapse core architecture, the only thing that we do is we merge the functions of these 2 layers into single physical device. So these 2 layers, that is the distribution and the core layer, will be combined into a single layer, and this is what we call as collapse core. So in collapse core there will be access layer, and distribution and core layer will be merged into one. So logically those layers will remain separate. Logically, what I mean is, so access layer will be layer 2. When it terminates on the collapse core layer, it will the layer 2 of the access layer will terminate in a layer 3 in the collapse core layer on the southbound, and on the uplink it will be L3. So finally we are having all the 3 functions, but the only thing is that we have combined the functions of the distribution and the core layer. Next we'll go to the cabling. What are the types of cables that you can use to interconnect networking devices? So Ethernet cabling, the first type of cable, there are 3 types of cable: straight through cable, crossover, and rolled cable. So we'll discuss them one by one. So first is straight through cable. So this is used to connect different devices back to back. So by different devices I mean host to switch, router to switch, and such other connections that maybe. So now, and the pin connections that are shown is 1, 2, and 6 connected back to back with the 1, 2, and 6 on the other end. So it is a straight through connection and straight pin to pin connection. So the important point here is the transmit pins on the host 1 and 2, and the switch the receive pins 1 and 2, and vice versa. So that makes the communication feasible between different devices. And this connection diagram is true only for 10 base T and 100 base T. Now what is 10 base T and 100 base T? So 10 is the range, 10 meters, 100 is the range, that's 100 meters. Base T, T is for its electrical and its electrical. So basically this is 10 meter electrical cable. This is electrical cable with 100 meter distance, so 100 meter and electrical. So 10 plus 100 Mbps, as well. Next, crossover cable. So crossover cables will be used to connect similar devices back to back. For example, switch to switch, router to router, hub to switch, router direct to host. So like in most of the cases, we connect host to a switch. But in cases where we'll be connecting a host directly to a router, then we'll be using crossover cable again. The pin connections are as shown below. That is, pin number 1, 2 will connect to 3, 6 and vice versa, 3, 6 to 1, 2. So the receive pins on 1 and 2, that will become the transmit pins 3 and 6. So receive pins should be 1 and 2, and hence they are connected to the transmit pins of the other end and vice versa. So the communication is feasible. Next, the two pair connections that we discussed are for the 10 and 100 Mbps Ethernet. But for 1000 Mbps Ethernet, we have 4 pair connections. So for straight through cable, the connection logic is the same. 1:1 connections from 1 to 8. So that will form a 1000 base T straight through cable. And crossover cable will have connections as below. That is 1, 2 to 3, 6 will remain same, and vice versa. The new pair would be 4, 5 to 7, 8 and vice versa. So additional pair transmitting data in the 1000 base T specification. Finally, rollover cable or rolled cable. This is used for console connections to router. So whenever we want to take a console connection from a router, we will have to connect the console port, the rollover cable, to our laptop or PC. And the connections, the pin diagrams are in the reverse, 1 to 8. On the other end, it will be exact reverse, that is 8 to 1 respectively. So, and finally, these are the settings that you'll have to do in PuTTY in order to take the console of the router. So baud rate to 9600 bits, data bits to 8, parity to none, and flow control options to none. So we also have fiber optic cable types. So fiber optic cable types which we use so they will follow the principle of guided light waves. So light waves will travel through glass or plastic, and those light waves will be used to decode the information that has been transmitted. So the core components of a fiber optic cable are core, cladding and buffer, as you can see in this diagram. So this is the core part, which you can see here, the center where the light waves undergo total internal reflections to be carried to the other end. The second is the cladding part, which is nothing but the outer covering which you see, and the third part is buffer, which is nothing but protection, for the purpose of protection. There are, even in the fiber optic, there are two types of fibers: single mode fiber and multi-mode fiber. So we'll go through a high level understanding of the difference. So in multi-mode fiber, the light waves can be carried in multiple modes. That is, what we mean is there are different ways through which the total internal reflection can occur at different angles. So completing all those permutations and combinations, we can have multiple sets of light waves going this way, which is shown in diagram 1. So the total internal reflections has to be satisfied, and then we can have a multi-mode fiber. So multi-mode fiber is it's susceptible to interference as well as its short distance. On the other hand, on the single mode fiber, only one single mode is carried. So only one way of carrying light can be used for single mode fiber. This is what they have shown, only one mode. And this single mode fiber is costlier and is used for long distance. So this was all about the cable types, the Ethernet and the fiber optic cables that we had. Next, we will discuss the topologies, various topologies that we can have. So it's bus topology, ring topology, star and mesh. So in the bus topology, as we can see, we will have a common shared media, and all the users will be connected to each other through that media. So what this means for user 1 is connected to user 2, 3, 4, 5, 6 directly. It's directly connected to 2, 3, 4, 5, 6. And the transmission over this media has to follow the rules of collision avoidance, because if any two users transmit simultaneously on this common media, there is a possibility of collision and data corruption happening on the link. So in bus topology, the rules of collision avoidance is to be followed. Next is ring topology, where a device is connected to back to back to other devices, and then the last termination is connected to the device itself. So this type of connections you will see in service provider industry. In service provider industry, you will have these as the access rings. So in access rings, maybe this is your aggregation router, you're connecting SAG1, maybe this is your aggregation router 2, and on the southbound we are having some access routers terminating to, for example, maybe access router 1, access router 2, and so on. So the ring can go on expanding as and when new routers are added, and the load has to be catered by the aggregation router to transmit data on the uplink. So this is ring topology. It's commonly used in service provider industry in the access layer. Then star topology. Star topology, this is what we have seen in connecting various users to a common switch. So this, for example, is the common switch, and these are the users, you can say. So this users connecting to a common switch, and then switch ultimately taking them to the next layer, say the core layer or the aggregation layer. That's star topology. More of a hub and spoke kind of. Next is mesh topology. In mesh topology, we have two types: full mesh and partial mesh. In full mesh, we have each device connected to every other device in the network. So in this case, if I have to a full mesh, then this link will connect here, 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 this link will connect here. So basically, every device will connect to every other device in the network. So this will be true for all the devices as well. So that is full mesh. And partial mesh is nothing but, for example, if I don't have this connection, if I don't have this connection, and if I don't have, for example, this connection. So this is partial mesh, where I'm not connecting to all of the devices, but maybe most or few of the devices in the network. So that's partial mesh. Finally, hybrid topology is nothing but a combination of all this. Maybe you can say a hub topology at one end, and it's connected to one of the member of the ring topologies, and further ahead it's going to the hub of the ring topology, star topology, sorry. So this we can have a combination of topologies, various topologies, to form the hybrid topology. So that's all for this chapter. Let me know if you have any questions in this chapter. Please post them on the forums. I will answer them as soon as possible. And I'll also be sharing mind map of this chapter, so for easier revision of the videos. So in this video I'm not added it, but in next video I'll share a mind map of this chapter as well as the next chapter. Thank you.